These are images from this recent article on single molecule microscopy by Rayleigh et al. In Nature Reviews. The single molecule part means that the light source is a single fluorescing molecule, although here the image is spread out over a wide area and many molecules are involved. It might be better to call this sparse molecule microscopy. But look at the resolution achieved. The wavelength is around half a micron, but here we see this scale bar is 2 microns. The filaments that are observed are on the range of 10 to 100 nanometers. Here we see the impulse response as a function of z for this depth resolved image at the lower right. And you see that the impulse response is much broader than the resolution achieved. Let's talk about how this is possible. Computational imaging. Episode 10, Resolution. We spent our discussion in this chapter talking about forward models, how we build forward models and how to evaluate forward models. So now we're ready to talk about what makes a good forward model. We talked about sampling with rectangular pixels of a band-limited function, and we derived this singular value spectrum, and we would say that the forward model, when we sample at Nyquist here or over Nyquist here, is better than the forward model when we subsample, where we have fewer singular values. We can also look at the singular vectors, the features that were measured, and we could say that if the features overlap the object, that makes a good forward model. Now, in the next chapter, we'll talk about forward models in the context of image estimation. But in imaging systems, oftentimes we talk about resolution as a metric for the quality of the measurements. So in this discussion and the next, we're going to talk about what resolution means. What is resolution? It has something to do with the relationship between the estimated object and the embedding space. Here, the embedding space would be along the x-axis, and we're showing the measurements, g, along the vertical axis. This is for 2 point targets that are each resolved as impulse response, which in this case is the unit sinc squared. And what we see in the curves as we go up in vertical position is more and more separation between the 2 point targets. So traditionally, a measure of resolution is the Rayleigh criterion, which would be to say at what point here, for what separation delta x between the 2 point targets, can we determine that these are 2 point targets? This is a question in estimation theory, and we'll talk about estimation theory in today's discussion. These questions are evaluated based on statistical analysis. It's not as simple as saying it looks like 2 to me. So this is one measure of resolution, but here's some illustrations of another measure of resolution. The image at the upper right is ChatGPT's idea of what the fiber internet looks like. When one installs a gigabit per second fiber line, this means that the maximum information data transfer is 1 gigabit per second. This comes from the Shannon limit, the time bandwidth product. In 1 second, the time bandwidth product is around 1 gigabit. Sampling at 1 billion times per second yields independent data. Now, the image at the right is from a 1988 version of IEEE Computer Magazine, where we're looking at the compact disc and the optical file cabinet. The space resolution is determined by the number of bits one can store on the disc. We save this version of resolution for our next episode. Let's focus today on the issue of estimation theory. So we're going to focus on resolution related to the Rayleigh criteria. Suppose instead of 2 point targets, we know that the target is a point source. Given a measurement like the one shown here, we want to say exactly at what value of x naught is the center of this position. Our resolution will be the standard deviation based on measuring the position or estimating the position of the source. We're going to use the likelihood function. So what we want to have is the likelihood of f given g. We want to estimate the underlying object state f given g. Now in this case, f is determined by a single parameter. We know the object, we're given a prior that the object is 1 point source, and we just want to know what is the position of that point source given our measurements. As suggested by the name, maximum likelihood estimation consists of choosing the value of f that maximizes the likelihood function. Now, in many cases, we choose to work with the logarithm of the likelihood function rather than the likelihood function. It behaves monotonically the same as the likelihood function, but is often, as we'll see, easier to calculate. So we're going to choose f to maximize the logarithm of the likelihood function. The likelihood function, let's say, has some structure like this. So this would be some parameters of f, and there'd be some maximum point here where the gradient of the likelihood function goes to 0, and we want to choose that point. If the curve is sharply peaked, then the odds that we're going to choose the right value would be high. We'd have some error, let's say, in f that would be proportional to the how sharp the gradient is, how sharp that peak is. So the Fisher information is used to evaluate the sharpness of that peak, basically. So the Fisher information matrix is the expectation of the product of the gradient of the log likelihood with respect to parameters f sub I and parameters f sub j. So the object, let's say, is described by some matrix of parameters, and we can build this Fisher information based on the product of the gradients of each of those. And the more sharply those are peaked, the greater the value of the gradients, the more information we would expect to be getting about the object. The power of the Fisher information comes from the use of the Cramer-Rao lower bound. One can show that for any unbiased estimator on G to estimate f, the covariance of estimates of f is going to be greater than or equal to the inverse of the Fisher information matrix. And in particular, the variance of the parameter f sub I is going to be equal to the diagonal term, the inverse of the Fisher information matrix evaluated at the diagonal term for that coefficient. So this gives us a bound for any unbiased estimator for what our error is going to be in estimating features of the object. So let's look at an example. Here we assume again that we have a single point source described by the impulse response h of x, x naught, and we want to know what is the position x naught corresponding to this point source. So the expected measurement that we would get for this distribution would be the distribution function times delta x. So over any interval delta x, the signal that we would expect to be measured would be the impulse response over that interval times delta x. We could assume any kind of distribution for our measurements, but let's assume that it's Poisson distributed using the Poisson distribution that we derived in episode 9. So here, this is the probability that we're going to detect n photons, given that our mean number of photons we would expect to detect is n bar. If we assume that our expected number of photons is this value at x, h of x, x naught times delta x, and our actual measurement is g, so in this case n is equal to g of x, and n bar is equal to h of x, x naught delta x, we have this distribution function for the likelihood that given our measurement g, our signal value is, the object state is x naught. So we can calculate the log likelihood for this distribution. We take the logarithm of the Poisson distribution, and we get this form. And now we're going to take the derivative of that with respect to x naught. So we have the derivative of the impulse response with respect to x naught. And because it's a log, we get 1 over the impulse response. The derivative of g of x, our actual measurement with respect to x naught, is 0. So this term drops out in the derivative, and we just have this term of h prime. Now we can take the expectation value of this with respect to this Poisson statistics. And so we're going to take the expectation value of the square of the derivative of the log likelihood function. And to evaluate this expectation value, we use the fact that the expected value of g squared is equal to the n bar squared plus n bar. So it's equal to the square of the mean plus the mean. When we substitute that expectation value in here, what you find is that the h squared would turn into just h, and then the terms in that are linear in h prime delta x times g drop out, and we get just this value for the expectation value of the gradient of the log likelihood with respect to x naught. That means that our Fisher information again is this product, but here we only have one unknown parameter, so the Fisher it's just a Fisher information value, not a Fisher information matrix. Using this expectation value, we can calculate the Fisher information, but this is the Fisher information at for one measurement at a particular value of x over the region x delta x. The Fisher information adds for a set of measurements, which in this case would be distributed over X. So we would integrate to get the total Fisher information as shown here. That was a general form for the Fisher information for any distribution. Let's assume as an example that we have this Gaussian impulse response h of x, x naught, and so we can evaluate the Fisher information matrix, or the Fisher information value in this case. So if we take the derivative of the exponential value, we get another exponential, so this would cancel into just a single exponential that we can easily integrate to get the Fisher information. In this case would be the amplitude of the signal, I naught, divided by the width of the Gaussian, or the variance of the Gaussian, sigma squared. That means that our Cramer-Rao lower bound for estimating x naught is sigma squared, the variance of the impulse response. So this would be, approximately of width sigma squared, divided by I naught. So I naught is the signal value that we've measured. So I naught basically would be, the peak photon flux. So the Cramer-Rao lower bound is not, our estimation accuracy here is not the width of the Gaussian, but the width of the Gaussian divided by the total photon flux. So if we measure, let's say, 1 million photons, that I naught would be a million, and so the standard deviation that we would see in our Cramer-Rao lower bound would be the standard, the standard deviation for the impulse response divided by the square root of 1 million, which would be about 1,000. So we could expect to be able to resolve 1,000 times narrower than the impulse response if we measured 1 million photons. In the example of single photon microscopy, what that means is that we can't observe one fluorescent photon from each molecule. We need to sit and integrate for some time so that each molecule fluoresces, and if it fluoresces 1,000 times, then we would expect to be able to resolve it 30 times better than the impulse response of the system using a maximum likelihood estimator. So we can't just simply treat our measurements as the measurement of the scene. We need to use some maximum likelihood estimator, which is what is done here to take the raw measurements, which are going to be blurred by the impulse response, and turn them into the fine filaments that you see. So this is a measure of resolution. So the key thing that we're talking about here is, what is the feature size that we can resolve from this system? We have a certain impulse response. The impulse response width is, let's say a wavelength. But if we integrate enough photons, then we can, and we know that we have a single molecule, so we know we have a single target, then we can resolve that target to much finer than the impulse response width might suggest. We're going to talk a lot about resolution in the episodes going forward as we get into talking more about physical systems. In every case where we talk about a real imaging system, we'll want to talk about the limits of resolution. This is one measure of resolution. Now, most scenes that we'll look at are not going to be these sparse filaments of single molecules. Most scenes are going to look like this, which is a scene that we looked at in episode 9. We're looking at a palm tree and a resolution target, and we zoom in and we see a certain feature size. Now, in episode 9, I mentioned to you that you can take this scene and use a neural estimator to improve the resolution, and you get this reconstructed scene rather than the blurred scene. Now, the point here is that this scene is also sparse in some basis. It's not sparse in the individual pixel basis, but it has sparse features. And if we look at these kind of features and can identify not, where's a single molecule, but where is that feature, we would expect that we have the capacity to resolve well beyond the diffraction limit, and that is commonly occurred, as we'll talk about throughout the course. And this is all based on, ideas coming out of estimation theory. When we estimate parameters in a scene, like where are the features in this scene, the computational imaging will achieve results that are better, much better than just looking at the raw data, as we'll see going forward. Now, the point of these scenes is that they're sparse in some way that allows estimation. There are scenes that look like this. So what if we have just uncorrelated data in every pixel? Another measure of resolution would be to say how much information can be communicated through a scene that looks like this. And that's a topic and a strategy for thinking about resolution that we'll talk about in the next episode.